Hi everyone, today we're looking at Leetcode question 33, search in rotated array. The question goes as follows. Let's say we had an ordered array of n integers. So here I'll denote them as x0, x1, all the way until xn minus 1 for a total of n ordered integers in this array. Now, I'm going to pivot this ordered array at some index k as follows. We take everything from index k onwards and put it in front. We put everything from index 0 to k minus 1 behind it, like so. This sort of array is what's given to us in the problem. Let's call it n. So given such once pivoted ordered array of integers, n, the question asks you to return the index of some target integer in n in logarithmic time. Here's an example. As you can see, the original array being 0, 1, 2, 4, 5, 6, 7 has been pivoted around 4, giving us the new array of 4, 5, 6, 7, and 0, 1, 2. If the target exists in this array n, we simply return its index. If the target doesn't exist in our n, we simply return -1. The trick with this question is not so much being able to find the right solution, but being able to find it in logarithmic time. In brute force, we could simply just iterate through the whole array and do an O of n search. However, our goal is O of log n, meaning that we have to implement binary search even though the array has been rotated once through. Let's see how we do that. In every single iteration of binary search, we first find the middle index. Let's call it m. There are 3 such possibilities. The simplest case is that we have found the target. In other words, nm is the target. We just return m. The second and third case are that n of m are greater than the target or less than or equal to the target. These 2 cases are where we differ from traditional binary search in an ordered array. Let's look at this case first, where nm is larger than the target. There's 2 possibilities: that our m index is part of the blue, or our m index is part of the green. Let's first look at this case right here, where our n of m is larger than our target and our m is in the blue part. For argument's sake, let's say m is somewhere here. Since we know this value right here at m is larger than our target, there's 2 places that our target could lie. It could either lie left of m until the left pointer, because everything here is in decreasing order, or if our target is even smaller than our left pointer, it means that it must be part of the index 0 to k minus 1, since all of these values here are lesser than the value here at xk, or at the left pointer. In other words, if the left pointer's value is larger than the target in this case, we search right of our middle pointer. Since we don't know where the x0 starts, m plus 1 is our best estimation. Otherwise, we search everything left of m. Now let's look at this case over here. If m is in the green portion, but n of m is greater than the target, so something like this pink m over here, then the only values in this array that could be lesser than our n of m has to lie here between x0 and m. since we don't know what x0 is, we just search everything left of m. Now let's look at the third case, where n of m is less than the target. Similar to the previous case, m could belong in the blue or the green areas. If we were here at this purple m, so somewhere in the blue, and our n of m is lesser than our target, the only place that target could possibly lie is between m and n minus 1, x of n minus 1 here. But since we don't know exactly where this pivot is, we just search everything right of our m. Now if m was part of the green portion, like here with the pink m, and our n of m was lesser than the target, there's two possibilities. One is that the target lies here between m and the right pointer, and the other possibility is that the target lies in the blue region, since everything here in blue is greater than any number here in green. Knowing that our target can lie right of m or in this blue region here, how do we discern which one we search? Similar to this case right here, what we do is we compare the end pointers of the array. We search this portion if the target is less than or equal to the value here at the right pointer, since the right pointer holds the upper bound for all the values here in the green. Otherwise, we search the blue portion. And as before, since we don't know where this pivot lies, we simply search everything left of our pink m right here if we know our target is going to lie in the blue. At the end of our searching, if L and R pass each other and we're done, and we still haven't found our index, then we know it doesn't exist and we return -1.
Now, if you're this far in the video and you like what you see, please give this video a thumbs up, a comment, and maybe even a subscribe so that you can tell YouTube that you like my content and you want to see more of it. Without further ado, let's begin. Let's walk through the code step by step. First, we declare n as the length of numbers, L and R as the left bound 0 and the right bound index n-1 accordingly. While L is less than or equal to R, we perform binary search. We find the middle by taking L and adding the difference floored instead of doing L plus R floor divided by 2 to avoid overflow when numbers are too big. Next, we have our three possibilities: that our nums mid is equal to the target, greater than the target, or less than the target. If it's equal to the target, we simply return our middle. Here's where things differ from binary search. So what happens when nums mid is greater than target? Well, we almost always move our pointer, right pointer, to the left side of mid. The only time when we don't do that is when we're in the special case of being in the blue side of the array, meaning the first increasing portion part, and our target is greater than that first left pointer there, meaning that we need to stay within this blue array or the first ascending sequence in the array to search for our possible target, meaning we shift our left to our mid +1 and keep our right pointer the same. The else case, when nums mid is less than target, is almost the opposite of that. So almost always when our nums mid is less than our target, we want to increase our L to mid +1, except for the special case when nums mid is less than or equal to nums r, meaning we are in the green portion or the righter ascending portion of the array, and nums r is less than our target, meaning that instead of staying in the green portion here, we actually need to search the blue portion on the left side. Move our right pointer to our mid -1. At the end of all this binary search, if we still haven't returned any value, we return -1, meaning that we could not find the target in the given nums.